start, before we start, there is a little comment, a gentle reminder, a web page in a BIMSA web page for the member seminar is updated. There are some information, especially for speakers. Please read it. It's a great pleasure to have Artan as our speaker, and he will talk about counting points and surfaces in dimensions 4, 6, 8, and 10.
Thank you. Thank you very much. Sergio says he's interested in dimension 12. Okay. So it's funny because I normally thank the organizers, but I am the organizer. So yeah. Thanks for having me. So let me tell you what research I do. I'm an algebraic geometer. What it is, it's the science of studying solutions to algebraic polynomials. Calculus is one example. Y equal to x, y minus x equal to 0. You graph it, you get a line. You can have systems of algebraic polynomials. You can graph them. You can look at intersections of these solution spaces. Interesting geometry can come out. In algebraic geometry, we don't work over only real numbers. We can work over complex numbers. We can work over number fields, arithmetic fields, algebraically closed fields, different kind of fields. For instance, when we work over complex numbers, this equation, we can x, y, z here are going to be complex variables. We look at solutions to those things. You get beautiful pictures like this. The modern algebraic geometry was founded by Alexander Grothendieck. He kind of taught us that, similar to manifold theory, where you can think of a manifold as locally as Cartesian spaces, and then by gluing these Cartesian spaces, you can get manifolds. Schemes, which are analog of the spaces in modern algebraic geometry, are somewhat locally looking like spaces given by solutions to algebraic polynomials. So schemes are locally look like the spaces that I just drew. So glue them together, you get more complex, more interesting, more exotic spaces. After construction of Grothendieck, thousands and thousands of pages, algebraic geometry found its way to other fields of science, theoretical physics, for instance, quantum gravity, topological string theory. I mentioned that as an example today. Mathematical neuroscience, artificial intelligence these days, believe it or not, and many other things. So algebraic geometry is a cool topic. It's kind of fit for understanding nature. And of course, I can defend my field, so I can brag about algebraic geometry. Anyways, but maybe from my point of view, it's interesting because nature and algebraic geometry, from my naive angle, at least have two common ingredients. Both of them care about relationships and deformations. Nature often is made of certain objects which always interact with each other, and often these objects evolve, like human cells are interacting with each other, neurons are interacting with each other. Nevertheless, neural system grows, cells grow, they die, they recreate many things. So deformations and relationships. Algebraic geometry has its in core two engines. One of them is the one that captures relationships, that's category theory. And the other one captures deformations. And that's what we call a fancy word for it, moduli theory. But moduli theory can be much simpler than just a fancy moduli spaces. It's an engine to understand deformations of algebraic objects. Now here is one example where algebraic geometry can come in. For example, one big question in theoretical physics is the merger between quantum mechanics and Einstein's theory of gravity. And of course, when we learn physics in high school, and I'm not even brave to say physics in this room because many of the people I'm looking at are experts. Anyway, but we learn physics in high school as this limit of physics where gravity is not merged with quantum mechanics. At least that's not how I learned physics. So this is a certain limit, but it's not quite true, physicists tell us. If you can merge these two things, it's a hope that you construct some theory called quantum gravity. And I emphasize it's a hope. At least from mathematicians' point of view, this has not been, it's not well defined. And it's supposed to explain the behavior of quantum particles in interactions with each other, relationships with each other. In the presence of strong gravitational fields, sometimes these gravitational fields might actually fluctuate. So these particles, which are related to each other, their relationships can deform under gravitational fluctuations. One place in the universe that this could be interesting, and with high school physics we cannot understand it, is when the particles fall inside the black hole. You have quantum particles, but everything is feeling the presence of a strong fluctuating gravitational fields. So that's what, again, experts are sitting in here. I don't dare saying anything more. So, all right. There are many mathematical models built for quantum gravity. The one I can talk about, or I can be brave enough to talk about, is topological string theory. If a mathematician tells you we understand a string theory, it's a lie. We don't understand a string theory. We cannot touch a string theory. It's not well defined mathematically. Topological string theory is something that at least I can say I can touch. So in terms of rigorous definition, mathematical definitions, topological string theory is the only thing that we can actually have some understanding. In all of these models, there is basically this proposal that our space, four-dimensional space-time, is equipped with extra dimensions. So maybe 6 dimensions, maybe 8 dimensions. There are some subspaces in them, say 4 dimensions. Then there are strings inside these subspaces or interacting between them, etc., etc. When I first watched PBS TV series on string theory, this was the explanation Brian Greene gave, and I understood nothing. So let me make it a little bit better. Let's say this is our space-time, and these are the particles. Of course, quantum field theory is all about particles coming together, interacting with each other. And Feynman diagrams and Feynman path integrals tell you about these interactions. So you have these particles, they come together from an initial state, the system evolves quantum mechanically to a final stage, and you would like to measure something about the system, let's say energy. So of course, I know physicists here are more experts in this, but if you're, say, someone not doing this, or you do biology, you don't care about quantum mechanics and so on, the very simple thing I can say is that, for instance, if I want to go from Huairou to Beijing, and I want to calculate how much fuel I need for my car, I parameterize my path from Huairou to Beijing, I integrate some measurable function that and I take into account traffic. So yes, and then I integrate this measurable function, liters of fuel per mile or per kilometer. I integrate, I calculate the energy. But if I'm a quantum particle going from Huairou to Beijing, I wouldn't know my path. So I might take many, many possible paths with some probability. So Feynman comes and says, okay, you can calculate the energy still, but you need to consider all the paths, and you need to take a stochastic average over all possibilities. So you might take this path, let's say 10% taking this path, 10% times the energy, parameterize, integrate, 5% times the energy, parameterize, integrate. So anyway, you can take an average. And roughly speaking, it tells you energy of the evolution of the system from initial state to final stage. So that's Feynman path integral. So you need to be defining an integral not over one path, but you need to be defining an integral over a space that parameterizes all paths. That's the essence of Feynman path integral. So same thing happens. Quantum field theory very successfully has been built on this, and the string theory is no exception. Now I would like to extend my universe with extra dimensions. This is my naive way of extending my universe. Space-time, I extended in vertical direction, say by 6 dimensions, 6 extra dimensions. Anything and everything, every being in our universe will have an extension in string theory. Particles also would have an extension. Now, in the picture that I'm drawing, these dot-like objects, which are our particles, have an extension given by some closed string in the Calabi-Yau direction. So if you look at PBS TV series, Brian Greene tells you that this extra dimension has its own geometry. And because of the gravity is very large, it warps this space. It's not R6 really, it's actually Calabi-Yau manifold. Okay, so I'm extending my universe in extra dimensions or extra directions. I have some very exotic manifold, Calabi-Yau manifold, and my strings are curves inside there. Of course, again, I could be wrong by saying that this is the only possibilities. Extension of the particles could be a curve that a part of it lies on the vertical fibers and a part of it goes on the even horizontal fiber. Of course, that's true. But the part of the type of the theory I'm interested in is that the projection of the particle on the space-time is somewhat massless. So this is string, the massive part of this string is only in the Calabi-Yau part, and that's what we are interested in. So I'm not interested in thinking of a particle as a bent rubber band, a part of which is on the horizontal base. It could be. Okay, anyway, so again, you're left to Feynman path integral. If I do that, now the path is that these closed strings, because it is very visual, right? The path is that the closed strings give you, which are called the string worldsheet, are tubular type surfaces like this. And these are actually Riemann surfaces. Over complex numbers, algebraic geometry thinks of these as algebraic curves. So Feynman says you want to integrate over a space that parameterizes all these possible paths. So you need to understand what is this space parameterizing these Riemann surfaces in an ambient Calabi-Yau manifold. So calculate, define an integral that gives you all of these. Okay. Maybe these paths have boundary conditions on D-branes, etc., etc. So the energy, the free energy of the string is given in terms of an infinite series. First time I was reading this thing, because I'm not a physicist, but I understand high school physics, yeah? So when I calculate kinetic energy of a mass going from point A to B, I get a finite thing. But here I'm calculating free energy and I get an infinite series. And of course, that's bizarre because here I need to be really looking at all possible paths. So that's the partition function that pops up in the string theory. Okay, so these empty block boxes somewhat need to be counting for me how many of these paths I have. So you have Riemann surfaces, and you want to look at the space parameterizing them, and you want to calculate one number on that space. It's not possible because, again, you have many types of Riemann surfaces. And what I mentioned about topological string theory being the only thing I can touch is exactly here. The Riemann surfaces can become as bad as possible. This is actually a very lucky situation that you have a smooth space like this. It can fold itself, it can intersect itself. The problem is that this measurable function, the one that was giving you liters per kilometer, gallon of the car, this measurable function cares about the geometry of the space, geometry of the path. If the path becomes singular, if the curvature of the space becomes really exceeding, then you will get your integral diverges up. So you need to kind of approximate, and the string theorist teaches me that you can approximate this, smoothen the path. So you're not really solving the actual string theory, you are looking at something called renormalization. So whenever your path becomes singular, smoothen it up, approximate it with a smooth path, renormalize the path, but then you cannot go so far from the path either. So you can smoothen the path, deform the path, but you need to keep the topology of the path fixed. So we are almost in topological neighborhood of the nice paths. And that's what topological string theory is. So I'm counting how many of these paths I have. I can deform them, I can smoothen them, but I need to fix their homology cycle in the ambient homology theory of the Calabi-Yau manifold. Okay? So this space that parameterizes these paths actually breaks into chambers. Depending on fixed homology class, there's a chamber of this space that parameterizes this homology. There's another chamber of this space that parameterizes this homology, so on and so forth. Each chamber is not one path. It's a family of paths. So your integral breaks into pieces. Each piece is an integral over the sub-parameterizing space, parameterizing Riemann surfaces with a given fixed homology. When you calculate these numbers over each one of the subfamilies, these are the numbers that fill in this empty square. Okay? All right, so I'm an algebraic geometer. First of all, it's okay if I call Riemann surface an algebraic curve. So I'm counting curves and points deforming in X, and each one of those numbers is some kind of an invariant I associate to the space parameterizing that algebraic curve with fixed homology. Okay, so this is the first thing. First nice paths are like this. There is a subfamily of the space that parameterizes nice, smooth algebraic curves of genus 0. And I can calculate that thing, let's say. So mathematician tries to calculate this number, and the physicist tries to calculate this number. Physicist uses something called geometric engineering to calculate this. So he looks at this space, he opens it up, he defines some way of calculating these numbers. Algebraic geometry does something else. It's called intersection theory. And I will tell you what intersection theory is. Okay, so algebraic geometry calculates, physicists calculate, these match. Then the path can become more exotic. It can develop some singular sharp edges, things like that. Algebraic geometry calls these mark points. Geometry calls these singularity loci, where the geodesics defined on this surface would have infinite lengths. Okay, so we don't have metric in algebraic geometry, so we don't use this metric description. Okay, so they calculate that. Then you can go to the other subchamber of the moduli. You make the homology of the possible family of paths more interesting. Genus 1 surfaces, genus 2 surfaces, and each one of the subfamilies you calculate these numbers, and one by one you try to fill in these boxes. Okay. The problem is that calculation of these invariants, these numbers, each one of these boxes are an integral over a moduli space or submoduli space, becomes harder and harder. Whether you look at it from physics point of view or look at it from geometry or algebra point of view. First, say for this first number, these two genus 0 ones, two Fields medals were given, Maxim Kontsevich and Maryam Mirzakhani. That's how difficult it is. Genus 2 invariant, it's known in the community of mathematics. You can count invariants of genus 2 Riemann surfaces in an ambient manifold or Calabi-Yau manifold, but no one actually did the calculation because these calculations often turn out boil down to some very complex combinatorial maneuvers, and it becomes very difficult. So mathematicians actually didn't calculate, but physicists succeeded to calculate. Physicists succeeded to calculate genus 3, genus 4, up to genus 52. And in fact, there is a conjecture that mathematician says, I know my way of calculating these numbers and counting these paths. You have your way. There's a conjecture that probably these match. The conjecture has been verified for genus 0, genus 1, nothing more. Okay? All right. One of the people who developed the machinery to calculate these count of these paths from physics point of view is sitting right here. Sergio Cecatti with his BCOV machinery, BCOV differential equations. Okay, so that's what it is. It gets difficult. We wanted to calculate energy of the string. How useful is it if I told you I calculated 53? Yes, I did calculate 53. What is the good for that? I mean, there's nothing good coming out of it because I didn't tell you anything, right? It's an infinite series. So should we stop in here? Mathematicians' approach actually is that maybe, even though we cannot calculate these numbers because of due to the difficulty of computation, maybe we can prove that there is some pattern between them, some formulae between them, which allows us to calculate any number in the sequence recursively by looking at finitely many few numbers in the beginning of the sequence. Think about Fibonacci sequence, 1, 1, 2, and so on and so forth. As soon as you give me 1, 1, and as soon as you tell me there is a pattern, this short program in the computer can tell me any number in the infinite sequence, right? Same situation. So is it true that the partition function of counting these surfaces as ambient manifold actually has such symmetry pattern, underlying symmetry pattern? This has been formulated in a famous conjecture of string theory called S-duality conjecture. Interestingly enough, again, physicists succeed in surpassing the mathematicians. And by the intuition they have about these energy functions and these entropies of these objects in higher dimensional spaces, extension of our universe, they say, if you calculate entropy of this supersymmetric object in 10 dimensions, I think that the partition function has this property that coefficient of it can be calculated having finitely many few coefficients. Okay, so that's called modularity. So the statement is that partition function of counting invariance of these paths has modular properties. But is it true or is it not true? In actuality, the only way you can gain partition function with modular property is that you count algebraic curves in the manifold X, but not all of them. The ones that lie inside the four-dimensional submanifold. So over complex numbers, this brown thing is an algebraic surface, 2 complex dimensions. This red thing is an algebraic curve. So if I count not all curves in X, but the curves that always and always and always lie in this algebraic surface, if I deform the algebraic surface, equations are given such that my curve also deforms with it, then the partition function of that subset of curves and points in X has modular property. Okay? So in the language of string theories, because many of them are sitting in here, the S-duality conjecture tells you that partition function of something called D4, D2, D0 frames wrapping this four manifold has modular property. Okay. In algebraic geometry, we say the curve lies scheme theoretically on the surface. That's how it is. Anyway, so you have ambient calabial manifold, you have algebraic surface, you want to count curves and points lying on the surface, deforming an ambient manifold. This is all you need to know for today's session. Keep that in mind, okay? This was conjectured by these physicists, Gaiotto, Strominger, Denef, Greg Moore. Some of them, their students are here. Oguri and Kamran Vafa. Calabial 3, surface in it, systems of points and curves on the surface. I want to count them and I want to prove modularity. Just to show you that these are not hand-wavy conjectures. You don't need to read this slide. Please don't. So just look at how long this formula is. This is how detailed the prediction of a string theory is. This made of complicated combination of J functions, Jacobi forms, theta forms, and so on. To me, this is outstanding that somehow conjecture can be made this precise. And many of these things were proven to be correct. Yes, some of it, yes. Okay, so we want to count curves and points lying on a surface in an ambient space. Could be complex 3-fold, could be complex 4-fold. Fact 1. These numbers, as I said, algebraic geometry says intersection numbers. You might have colleagues in your departments, algebraic geometer, who says, I do intersection theory, I count things using intersection. Intersection of what? Intersection as follows. Let's say this space is one of those subchambers. I have a subchamber of my moduli space, let's say parameterizing Riemann surface of genus 0. These are algebraic curves, and I want to count the ones which are holomorphic. So there is a map from curve to ambient space X, and I want this map to be holomorphic. All I need to do to geometrize this counting problem is to think about a bundle, I call it E, whose fibers are antiderivative of this map F. This bundle comes with a section. In the locations where the section hits the base, antiderivative vanishes. And that's exactly locating for me the map from C to X, where C is holomorphic, where the map is holomorphic. So intersection is in this regard. Always you have some space parameterizing your paths, your Riemann surfaces. You have some bundle whose fibers are giving you obstructions to that path to satisfy certain property you want. This was the example for holomorphicity. It could be different things. So this is an obstruction bundle, and it has a section, and the intersection of that section with the base is the count. Okay, what if that section is not transverse to the base? Differential geometer has their own way of remedying this. Algebraic geometer has their own way of remedying this. Differential geometer says if the section of the bundle is not transverse, I perturb it, I make it transverse, then I count. Algebraic geometer says, oh, I don't understand intersection. I do everything with homology and cohomology. Intersection means collapsing homology class with cohomology class. So I keep the section, but I change the homology class of the base. Let's say fundamental class of the base is given. I produce some other cycle out of that fundamental cycle, fakely, such that intersection of homology class of this M prime with the cohomology of this bundle is a finite number. This homology class is fake, it's virtual. It's the virtual version of the fundamental class, and it is indeed called virtual fundamental class. So algebraic geometer has a way of making this section transverse and counting intersections. Differential geometer has their own way of doing it. Okay. Fact 2. Let's say you count these intersection numbers. That tells you the count of nice algebraic curves in the ambient Calabi-Yau manifold, right? You're not overcounting things. The machinery is set up as in a way that you're counting these things up to automorphism. So if there are, with fixed homology, multiple paths satisfying holomorphicity, for instance, you're counting them, then you divide by the group of automorphisms. What does that tell you? It tells you that when you calculate these numbers, when Chekati comes to me and say, Artan, what number did you calculate? How many of these paths after all you have? I said, well, genus 0 was 1/5. Genus 1 is 2/7. Genus 3 is 13/27. It's not enumerative. If I give you a number 1/5, would that tell you how many paths are there? No. Maybe it's one path with 5 automorphic copies, 2 paths with 10 automorphic copies. It's not enumerative. So even if you followed the nose, you calculated infinitely many numbers. These are rational numbers called Grama-Witten numbers. And these Grama-Witten numbers are not enumerative. They are not good for string theories. They don't count curves. They don't give you much information. The idea was then, again coming from physicists, that maybe underlying this infinite sequence of rational numbers, there are some infinite sequence which actually count curves. So they are integer values. How would you achieve such a thing? You cannot change your counting problem. You need to count the same thing, but you want to calculate an integer out of it. Well, maybe you can change your point of view. Count some object that represents this curve inside X, but it doesn't have higher automorphisms. Maybe. That's the solution, right? Well, algebraic geometry 101 that you teach in undergraduate tells you that such a thing exists. If a curve goes to X, it's the same as looking at regular functions on X, which vanish on the curve. Zero set of functions vanishing on the curve is the same thing as the curves embedded in X. So instead of counting curves in X, which have higher automorphisms, I count these modules. It's called ideal. If you took abstract algebra, you don't need to necessarily. These are modules. These are elements which are simple in their own algebra. They don't have higher automorphisms. If you count ideals of functions vanishing on the curve, whatever that intersection number is, it's going to be integer valued. These integer valued numbers are called Donaldson-Thomas. Okay, so Donaldson-Thomas theory came as a way of giving meaning, enumerative meaning to Grama-Witten theory. Okay, the space of functions vanishing on subspace of a given space X is called Hilbert scheme. Okay, this is an example. I can look at the surface. I can look at a bunch of points on that surface. Hilbert scheme can be constructed. It's a space that looks at functions vanishing on configurations of points with multiplicity. It's called Hilbert scheme of points. I can have Hilbert scheme of curves with fixed homology class. I can have Hilbert scheme of points and curves, right? The space of functions vanishing on points and curves on the surface. Okay. The person who constructed Hilbert scheme for the first time again is Grothin. He was trying to parameterize closed subspaces, subscheme subspace, same thing, subspaces of projective space. He realized that you can look at functions vanishing on the subspace and construct functorially some space out of it. After Grothendieck, these Hilbert schemes became absolutely fundamental object in the world of algebraic geometry. Many people worked on it. Example, Hartshorne. His textbook these days is being taught in graduate school to teach students algebraic geometry, kind of summarized EGA. He studied deformation theory of Hilbert schemes. Nitin Nitsur, Indian mathematician, still in India, functorial construction of Hilbert schemes. This is Don Zagier. He studied combinatorial aspects of Hilbert schemes. Manfred Lenn in Germany, in Mainz, studied topology of Hilbert schemes. Lothar Goethe became famous. He computed petty numbers of certain Hilbert schemes and their partition function. This is Richard Thomas as in Donaldson-Thomas theory. He actually set foundations of Donaldson-Thomas theory in his thesis. Andrea Kunkov taught us how you can bring statistical mechanics, methods of statistical mechanics, stochastic averaging, into counting problems in algebraic geometry. Use those methods on the Hilbert scheme of functions vanishing on subspaces, compute these partition functions. Pandey, he collaborated with him on many, many projects. Donaldson himself, together with Richard. And many other people did, and then came on the very tail of these amazing discovery and efforts came us. So past 15 years, I've been working on these things, 7 years of which was I had the pleasure of working with Professor Yao. Absolutely took advantage of his brilliant ideas. So let me tell you some of the things we did on computing these invariants using integrals over the Hilbert distance. So goal is you have system of curves and points lying inside an algebraic surface. Algebraic surface could be in a complex threefold, could be in a complex fourfold. A priori, threefold and fourfold might not talk to each other, but if you count same objects inside both, you might actually establish dualities between their corresponding string theories, and that's something actually we proved. Okay, so this was the goal. So this is the first project we did. That's Amin Ghulampour in Maryland, and this is Richard Thomas. So we were looking at some ambient Calabi-Yau manifold with the surface absolutely deforming on it, counting curves and points by looking at corresponding Hilberts in calculating these numbers. We calculated infinitely many of those boxes, but we couldn't fill them all in because it was very difficult. So we couldn't prove modularity, yet we learned a lot from that geometry. Later we realized this conjecture of a string theory is absolutely difficult. But if I restrict my geometry a little, maybe I can prove modularity properties. So we looked at another threefold. Let's say a surface vibration over a curve. Fibers are two-dimensional, base is one-dimensional. Curves and points still need to lie on the surface. This is the picture. The surface can deform, of course, but not just freely roaming inside X. It's deforming where it can deform. In its own zip code, it can deform. Yeah? We calculated partition functions of these invariants. We precisely proved conjecture of string theories. Modular form we got exactly matched in the level and in the weight with this partition function of string theories. Later, this was a smooth vibration. Later, with Yokinobu Toda, we allowed the fibers to be singular. We obtained the partition function. We also saw that this partition function, this modular form, is something known, Kawai-Yoshioka formula. So he showed that this actually does have the nice properties. Again, the string theories turned out to be correct. Later, long time after, I somehow, in a very labyrinth way, I found my way because I was collaborating with Melissa Liu, who is at Columbia University, former student of Professor Yao. Melissa had a problem to solve, suggested it to me. Then I got introduced to Professor Yao, and we started working on this project together with Sergei Gukov, who's at Caltech these days. So we have the curves and points again, lying on the surface. This surface is inside the non-compact threefold. It's total space of some line bundle. We computed modular forms, but that was not the point. We conjectured that invariants of these things are related to Seiberg-Witten invariants of this surface. So Seiberg-Witten invariants, for those who know it, count as spin structures on the surface. Okay, so this was a conjecture. Later, we proved this conjecture by showing that invariants are related to Seiberg-Witten invariants plus quantum correction terms. These quantum correction curves indeed count points and curves on that surface, but more. So it's not just points and curves, it's the flag of points and curves. So not only you can count curves and points, you can count curves and points sitting inside curves and points sitting inside curves. So this is called nested configurations, nested Hilbert disk, parameterizing this system, this flag. So you can compute intersection numbers over this flag moduli space. That's the left-hand side of this equation. And you can see that it's, that's this guy. That's actually this guy. You can see that this guy plus Seiberg-Witten invariance becomes interesting invariant. And those are Waffa-Witten invariants. So Waffa and Witten has some differential equations. Count of solutions to Waffa-Witten equations turns out to be equal to Seiberg-Witten invariance plus nested Hilbert scheme. Later, we said, what if curves and points sits in a threefold? And the threefold is deforming the Calabi-Yau fourfold. So with Diaconescu and Rutgers, we developed some machinery for that, threefold versus fourfold, and we computed some, in some cases, modular forms. Until now, so we have this non-Calabi-Yau fourfold. We are interested in fourfold these days. Non-Calabi-Yau fourfold, for instance, this is an example. Surface vibration over a two-dimensional base. Surface is, again, deforming not so freely. Curves and points are lying on the surface. We are trying to calculate partition functions. We are getting very interesting new modular forms. This guy is Jung-Suk Oh in Imperial College. Soon will be in Korea. And this is Nikita Nekrasov. I'm Professor Yang. So upper part of this diagram is counting points and curves on surfaces alone. And then this, what's happening? Is there a mirror here? Okay. Left part is threefold, right part is fourfold. As I said, if I'm counting same thing in ambient geometries, maybe there are dualities between their string theories. Any arrow which is filled is proved. Any arrow which is dotted, it's not proved, it's work in progress. So you can see there is enough to play with and get busy with. Fivefolds. Can I count curves and points in fivefolds? It's a question as open as this ocean. We know nothing of it. I stop here.
About fivefold because you have no conjecture from physics.
You can say that, but there is a conjecture from Akunkov and Nekrasov, who calculated partition functions of these in a very particular fivefold, which is a Calabi-Yau 3 fibration over a K3. There is a conjecture. The reason we don't know it is because developing the machinery of intersection theory over this modularized is impossible at the moment. But as soon as we can develop it, then we look at physicists again. We try to see if we can learn something.
Hi, Artan. Thanks for the really interesting talk. I just wanted to ask about the about the partition function that you'd computed, which was not quite modular.
It's not modular.
Yeah.
Yes,
So-
I lied to you.
But
It's mock modular.
well, that kind of answers
It's
my
written in terms of some complex variable.
uh-huh.
This complex variable lives on the upper complex half plane. Upper complex half plane is being acted on by SL2Z. And modularity is given via this action of SL2Z. But it's mock modular because I can only see modularity when I add the anti-holomorphic partner of this complex number. Then I can see modularity. You're right.
So, good. Actually, then you answered my first question, which was exactly how it fails to be modular. So it's more modular.
Mm-hmm.
But do you have an understanding of which PPS states contribute to the modular to the mock modular part only?
Yes,
I
the
see.
D0 brain states.
I see. Because the reason why I was asking is that in D1, D5, n equal to 4 compactifications, because of work of Zagier with Dabolkar and Murthy,
Yeah.
there is an understanding that only the single center black hole degeneracies contribute
That's
to the
correct.
mock modular form, and all
That's correct. When you're counting D4, D2, D0 in that language, if the mock modular form is a vector valued modular form.
Right.
The vector valuedness of it is because of the D2 brain contributions, and each piece being the scalar valued mock modular form is because of the D0 brain contributions.
Thanks so much.
Other question? Comment?
Professor, can I ask a question? Do you work on complex field? If I work on finite field, what if?
Well, there are some conjectures about partition functions over finite field, which actually give you modularity. I was just learning this from somebody today. You were telling me. So there is a partition function counting Schubert cycles over arithmetic fields that actually can be really realized similar to this, some kind of machinery of intersection theory over arithmetic fields, and this partition function has modular properties. But this is something that I'm also very interested in. I haven't learned much, so I cannot say more.
Thank you very much.
Thanks for asking.
Questions? Postdocs? Artan, can I ask something? Very stupid
Microphone.
question. I understand why you're interested in Calabi 3. It's a target space of a topological string. But do you have any other mathematical motivation for using Calabi 3, Calabi 4?
Yes. The reason for Calabi 3 is because of that bundle. When you look at that bundle, Calabi 3 property actually tells you that, virtually speaking, the section of that bundle intersects the base at a bunch of points. The virtual dimension of your moduli space is the dimension of tangent space of the moduli space minus dimensions of fibers of that bundle. When you have, correct. So it's virtual dimension 0 because of the Calabi property. So dimension of tangent space and obstruction space is equal. This is the mathematical reason. That's not. Well, that's the physical answer. But I said dimension of tangent sheaf and obstruction sheaf are the same. Okay, it's physics. Then it's physics. Then I cannot say something on top of Sergio Chikali. He knows better. Yeah, isn't it? Maybe. Yes, I agree.
Physics was in co-dimension, mathematician look floating. And now mathematician look to co-dimension and physics floating. And that was what it was asked. Why geometry is not in all dimensions and just physical? And can say because of the idea.
Yes. It's true. The answer I give you is in terms of the ranges I use to compute these numbers. When the space is Calabi, the range works. When the space is non-Calabi, hardly works. Sometimes works, sometimes doesn't. K3 fibration, threefold I told you, that's non-Calabi. It's not, but it works. K3 fibered fourfold, it's not Calabi, but it works.
Yeah, so can you maybe say or say a few words about the main difficulties in applying the machinery we have now for fivefolds?
If you're looking at moduli space parameterizing sheaves, the deformation theory of this moduli is given by self-extensions. Now, this is I apologize to the non-algebraists. You have a sheaf F, coherent sheaf F. Think about a bundle. Deformation theory of this bundle F is X1 F comma F. Obstruction is X2, but then there is X3, X4, right? This four-term thing needs to become two-term thing, and we don't know how to canonically make it a two-term. Because there's just too many cohomologies which are non-vanishing, and we cannot get rid of those things. In the threefold situation, we know how to cut it in half and make a nice space out of it, nice intersection theory out of it. In fivefold case, we don't yet know how to do it. You need to have some construction. You can have this space. There is no problem in constructing this space. You can intersect the section of this bundle with the base. You can. This number you calculate is not deformation. If the space, if the underlying manifold, X, which is fourfold, changes, your number changes. And so it's useless. Correct. Absolutely. Yes. You have the possible space of deformations of objects that are being parameterized by a space. This deformation sheaf, tangent sheaf, is not a bundle. It jumps in dimension. Okay. Yet there is some other bundle who's also jumping dimension. That's the bundle E I mentioned to you. Okay. The difference of dimension of fibers of tangent and obstruction is constant. So if out of these kind of, roughly speaking, difference of the two, you can construct a cohomology cycle and intersect with that, you will get hopefully deformation invariant. Each one of them jumps. but the difference doesn't change.
Uh, I have sort of a naive question that you you look at certain intersection points, and those intersection points turn out to be the coefficient of certain modular forms. That is what I got from the talk.
Correct.
The geometric spaces that you consider have their intuition or have their origin from certain ideas in string theory, right?
Mhm.
So my question is, what if you start with some arbitrary geometric setting where all these questions make sense,
Mhm.
and then you do the counting, you still get a modular form? So
Yeah.
uh,
Yes, it was great in my opinion, and I'm still young, and I shouldn't say that, but let me just make a brave comment. It's still great that string theorists came around and taught us these conjectures, amazing things. But of course, enumerative geometry, counting invariance over parameterizing the spaces, is an old question. Italian school of algebraic geometry even was interested in this. Yes, in fact, there are here and there in the corners of algebraic geometry where some modular form property was actually being predicted. But when the string theorists came studying these systems, suddenly it was like a revolution. So,
do you know any explicit conjectures or someone who has done calculations like explicit level? Do you know, like,
outside of the world of physics,
Mhm.
well, people were counting, for instance, certain secant lines, a line in a variety with certain tangency structures towards some subspace of that variety. Yes, there's examples like that. But I need to look.
These sort of correspond to modular forms.
Yes, yes.
Okay, thank you.
There are some examples. I mean, this enumerative counting things is a very, very big problem. I think even Khwarazmi was looking. Khwarazmi in how many years ago? 5 centuries ago. Yes. Khayyam also looked at it. But know nothing about modularity. Of course, just counting, computing 1 or 2 intersection points, yeah, in families. Yeah. Yes, using localizations. Even though the moduli space will become open and non-compact, therefore, on an open thing, you cannot define an integral any way you want to define it in an intersection theoretically. There's always, in these situations, a torus or something roaming around that has a fixed locus inside this open space, which is compact. And then the integral over that compact torus fixed locus. No, everything. Dimension on C2, on C4, Calabi-Yau 4-dimensional C4, Calabi-Yau 2-dimensional C2. Non-Calabi-Yau, it's okay. Non-compact is fine as long as you can use some torus localizations.
Sorry, just one more question. Probably pestering you at this point, but do you know of any examples of such a counting problem where the result doesn't correspond to a modular or a mock modular form?
Does not correspond.
Does not, where there is no modularity.
Gorama-Witten invariance. If you're counting curves freely roaming inside the Calabi-Yau threefold, the sequential Calabi-Yau threefold, about which everyone was excited and it still is, that's not a modular problem. Somehow surface is very important. Having a scheme theoretic support on the surface, or the language of the string theory is wrapping a certain 4-dimensional real manifold is very important.
More question. Oh, there is no more question. Let's close it. Yeah.
My ocean, did you